Hello and welcome to another NGen Math 6 lesson by eMathInstruction. My name is Kirk Weiler and today we're going to be doing Unit 5, Lesson 6, more work with equivalent expressions. Now it's pretty important, if you haven't actually already worked with equivalent expressions, especially our own Unit 5, Lesson 5, make sure to actually do that lesson because today we're going to be doing some slightly more advanced work with equivalent expressions, and we're going to start off with some review. Actually, about half the lesson is going to be review because it is so important. This idea of two expressions that have the same value always, no matter what value of the variable you put in. So let's get right into it in the first exercise where we do a little bit of review. So two expressions are equivalent if they are equal for every value of their variable or variables. Exercise number 1. Given the binomial, meaning two terms, expression 5x plus 15, do the following. Letter A, write this expression in factored form as a product of its GCF and another factor. Write all factors of this expression. All right, let's do a little bit of review. So when we look at an expression like this, we can see that it's got two terms. We can see that it's got two terms because it's got a single addition, so it has a term of 5x and a term of 15. All right, therefore it's called a binomial. Bi meaning the word two, bicycle, things like that, right? So we want to write this expression in factored form. That means we look at the 5 and the 15 and we think, what is the largest number that divides into both 5 and 15? That's pretty easy. It's 5. So the GCF in this problem, or in this expression, the GCF is equal to 5. So we can write this expression as a product. Let me just bring this up a little bit. 5 times what? Well, again, I want to think about what I'd have to multiply 5 by in order to get that expression. Well, I'd have to multiply 5 by x in order to get the expression 5x, and then I'd have to multiply 5 by 3 to get 15. So this is an equivalent expression in factored form. But how do we know it's equivalent? Well, that's what letter B kind of gets at, so let's take a look at that. Letter B says test the equivalency of the original expression with the one from A by testing x equals 2. All right, so let's talk about this a little bit. I should be able to grab any value of x, 2, 10, 2,000, it shouldn't matter. And if I put it in this expression and I put it in that expression, they should give me the same value. So what do I test? I test something nice and small, x equals 2. So what we're going to do is we're going to throw it in this expression first, then we're going to throw it in this expression, we're going to make sure the two are equal. Let's do it in that one first. Here we go. Test in 5x plus 15. This is simple enough, right? I want to show the substitution, 5 times 2 plus 15. 5 times 2 is 10, right? Then I do 10 plus 15, and I get 25. All right? Now, I also want to test it, though, in this expression. All right? And hopefully, I also get 25. So let's do it. Put it in here. This is going to be equal to 5 times the quantity, 2 plus 3. Obviously, order of operations now says we have to do that 2 plus 3. That gives me 5. And 5 times 5 is 25. All right. Now again, as we talked about in the last lesson, this doesn't prove that the two expressions are equivalent. But certainly, had we gotten two different answers here, that would have told us that we probably made a mistake in what we were doing here. Or maybe we made a mistake over here. That's the hard thing about mistakes. You never know quite where you made them. All right. So, two expressions that might look different but give us the same values. So, exercise number 2. All right, write each of the following binomial expressions in factored form, then identify the two factors of the expression. And I apologize because in exercise number 1, there was something that I left out. Let me just go back there really quick because it's part of this problem. In letter A, it said write all factors of this expression. So, factoring, right? Factoring just means to break something into a product. So for instance, if I have 12 and I write it as 3 times 4, I have factored the number 12. And the two factors are 3 and 4. All right? On the other hand, when I factor 5x plus 15 into 5 times x plus 3, the two factors are 5 and x plus 3. 3. And if you want, you could even put the x plus 3 in parentheses to really kind of hammer home the point that the two factors are this and all of this, right? I don't want you to think there's three factors here, 5x and 3. There aren't. It's 5 and x plus 3. That being said, let's now take a look at exercise number 2. Write each of the following binomial expressions in factored form. I know I read this already, but why not? Then identify the two factors of the expression. All right, so this is simple. It's really literally what we just did. So if I look at 8x plus 14 and I think about the numbers 8 and 14, I think, hey, what's the biggest number that divides into both nicely, right? That ends up being just the number 2. It's tempting to think it's the number 4, but 4 does not divide into 14 evenly. So the GCF is just 2. All right, its factored form would be 2 times 4 gives me the 8. X comes along for the ride. And 2 times 7 gives me 14. So here's that factored equivalent form. The factors then are 2 and 4x plus 7. And again, the parentheses aren't necessary, but I like to actually kind of put them in just to emphasize the fact that all of this, 4x plus 7, should be treated as a single thing. All right, so what I'd like you to do is do the same thing in letter B and letter C. Pause the video now and take a few minutes. All right, the GCF of 30 and 12, finally one that's a little more meaty than 2. The biggest number that goes into both 30 and 12 is the number 6. All right, that's the GCF. In factored form, we would then have 6 times 5 would give me 30. N comes along for the ride, as does the subtraction. And then 6 times 2 gives me 12. So there's my factored form. And my factors are 6 and 5n minus 2. All right. And hey, we shouldn't always do them with just a single variable. Here's one with two variables, an x and a y. If I look at the 6 and the 9, the largest number that divides into both of them evenly is the number 3. So the GCF is 3. In factored form, we would have 3 times 2 gives me 6. X comes along for the ride. 3 times 3 gives me 9. Y comes along for the ride. There's that factored form, 3 times 2x plus 3y, with factors of 3 and 2x plus 3y. All right. Factors are actually very, very important. You're going to see some really cool stuff, especially in Algebra 1, where just knowing what the factors of an expression are tell you a lot of important information. All right. For now, let's move on and do a little bit more work with equivalent expressions. Here we go. Exercise number 3, a nice little applied problem. A rectangle has an area given by the expression 14x plus 35. If the width of the rectangle is 7, then give an expression for the length of the rectangle. All right, awesome. I'd like you to pause the video and think about how you could sort of find what should replace the question mark, right? What is it that is the length, the missing length of this rectangle? And, spoiler alert, it's going to have an x in it. So pause the video now and see if you can figure out what that expression is. Well, we should know that the area is width times length, right? We should know that for any rectangle, area equals width times length, or length times width. Doesn't really matter. Now, we know that the area is 14x plus 35. We also know that the width is 7. So the question is, what's the length? Well, really, this is a factoring problem, right? I want to rewrite the area, 14x plus 35, as an equivalent expression that involves the product of 7 along with something else. Well, 7 times what gives me 14x plus 35? 7 times 2x will give me 14x. And 7 times 35, or 7 times 5, sorry, will give me 35. So this must be the length. Given that width times length is always area, that has to be our length. All right, kind of a nice problem that combines algebra with the area of a rectangle. All right, Now what we're going to do though is we're going to move on to a new thing when it comes to equivalent expressions, something called combining like terms. Very important and also pretty easy. So let's take a look in the next problem. All right, consider the following expression in exercise 4. Consider the expression 7x plus 3x. Letter A asks us to evaluate this expression for x equals 2 and x equals 5. Show your work. All right, easy enough. Let's do this. Let's together figure out what the value of this expression is when x is equal to 2, then we'll have you do it for x equals 5. So for x equals 2, really simple, right? What am I going to do? Well, I'm going to put the 2 in for the x in both places, so 7 times 2 times 3 times 2. 7 times 2 is 14, obviously. 3 times 2 is 6. And ultimately, we get 20. All right, easy enough. What I'd like you to do is pause the video really quickly and do the same thing when x is 5. All right, let's go through it. So when x is equal to 5, we're going to do exactly the same thing. We're going to have 7 times 5 plus 3 times 5. That's going to be 35 plus 15. And 35 plus 15 is 50. All right. Now, what's the point of this? Well, letter B. Based on your answer from A, what is this expression equivalent to? Explain why this must be the case by expanding, we'll talk about what that means, expanding the terms 7x and 3x. Well, take a look at this. When 2 went in, 20 came out. And when 5 came in, 50 came out. So it appears that this expression is equivalent to what? Pause the video and see if you can write down what this expression is equivalent to. Well, it appears like it's equivalent to 10 times x, right? Because 10 times 2 is 20, and 10 times 5 is 50. So it looks like 7x plus 3x appears to be 10x. Now, this is pretty easy to understand why this is, right? Because what is 7x? And this is what we mean by expanded form. 7x is the same as x plus x plus x. You get the idea. After a while, it's just going to sound funny to me, right? There's 7 of them, right? And 3x is going to be equal to x plus x plus x, right? 3 of these things. So it probably stands to reason that when I add 7x's to 3x's, in total, I get 10x's, right? And that's what it means to combine like terms. When I have 7x plus 3x, I've got 10x. That's what I have, because all I'm really doing is keeping track of how many x's there are. Multiplication is repeated addition. I'm adding 7x's together, then I add 3x's together, and when I add them all together, I'm adding 10x's together. It's really that easy combining like terms. So let's get a little practice on it in the next exercise. Here we go. Combining like terms. Exercise number 5. Rewrite each of the following expressions as equivalent expressions by combining like terms. So it really is this easy. I'm not going to write things out in expanded terms. 8x plus 7x literally is the same as 8 plus 7, and you don't even have to write this step out, times x. It's 15x, right? That's all it is. I am simply adding the coefficients on the x, right? Remember that term? Coefficient, the number that's multiplying the variable. And all I'm doing is adding the coefficients. 8x plus 7x is 15x. And it works exactly the way with subtraction, right? So if I have 22y minus 10y, what I really have is 22 minus 10 all times y, and that's going to be 12y. Ah, so easy. Now, this is where it can be confusing. All right, 4x plus 8y plus 10x minus y. All right, look, if I've got 3 apples and I add 4 apples, I have 7 apples. That's what I have. 3 apples plus 4 apples is 7 apples. On the other hand, if I add 4 apples and 8 oranges, I don't have 12 apple oranges, right? I certainly don't have 12 apples or 12 oranges. I've just got 4 apples and 8 oranges. So I can't add 4x and 8y. I can't do it. There's no way to combine those. But addition has this fantastic property in that we can rearrange it. In other words, I can rewrite this as 4x plus 10x plus 8y minus y. And now I can say, well, 4x plus 10x, that's 14x's. Then I can say, well, I have 8y minus 1y, and that must be 7y. Okay, so if the variable of the term is the same between the two of them, they're like terms, and you can combine them by combining their coefficients. On the other hand, if the two variables are different, like x and y, you can't combine them. If this was simply the problem 4x plus 8y, and I said write it in simplest terms, you'd be done. There's nothing else you could do, all right? You couldn't combine the like terms. All right, only combine two terms if they have the same variables raised to the same powers. For now, you don't have to worry about that same power thing because we won't get into that so much in 6th grade. All right, let's keep going with combining like terms. Now, we can get a little complicated with these. Let's take a look at that in exercise number 6. Consider the more complicated expression 2 times the quantity x plus 3 plus 5 times the quantity 2x plus 1. Letter A says use the distributive property and combine like terms to write this expression as the sum of only 2 terms. All right, so this is kind of cool, right? We can rewrite this using the distributive property, and we can rewrite this using the distributive property. And then we can combine like terms. So let's do it, all right? Let's kind of do this together because this is a little more complicated. I'm going to distribute through on the 2. 2 times x is simply 2x. 2 times 3 is 6. I almost didn't put a 6 there. Plus. Now let's distribute the 5. 5 times 2x is 10x, because 5 times 2 is 10. And then 5 times 1 is 5. So keep in mind, all I've done here is the distributive property. Now I want to combine like terms. Now 2x and 10x are like terms. And 6 and 5 are like terms because they have no variable attached to them. So I'm going to actually rearrange this a bit and rewrite it like this. All right, and now, just scroll this up a bit, 2x plus 10x will be 12x, 6 plus 5 will be 11, and there is my simplified expression. Right? I use the distributive property to come up with 2 expressions that are sort of equivalent to these 2 expressions, and then I combine like terms. Now, have we done it correctly? Well, that's what the check in letter B is about. Letter B. Test the equivalency of the 2 expressions by checking with my favorite number and yours, x equals 2. All right, so this is going to take a little bit of time, but let's take x equals 2 and let's plug it into the original expression. It's going to actually be quite quick to do it down here. This one's going to be a little bit of a pain, so let's start with that one first. I always start with the bad one first. I'm going to substitute it into this expression. Let's see what we get. All right, we're going to put 2 in for that first x. Then we're going to hopefully put a plus symbol down. There it is. I'm having a problem right here on the board. Then I'm going to have a 2 in for the second x. Then I'm going to erase that 5, which almost doesn't look like a 5. Ah, there, it worked just fine. Okay, let's keep going, evaluate what's in parentheses. 2 plus 3 is 5. In this one, we're also going to have a 5 because we're going to have a 4 plus 1. So that's going to give me 2 times 5, which is 10, plus 5 times 5, 25. And that's going to give me, 35. All right, so that's the original expression. Took me a little while, but the original expression when x is equal to 2 gives me 35. Now, much faster, let's substitute it into this expression. So down here, right, we'll do 12 times 2 plus 11. 12 times 2 is 24, and 24 plus 11 is 35. All right, good check. Looks good. All right, and that's about the most complicated kind of equivalent expression problem that you're going to see pretty much in this course. All right, let's wrap it up. So in this lesson, what we did is we worked more with equivalent expressions, two algebraic expressions that, although they might look different, think about that last problem, that very complicated original one and that fairly simple final one, right? Two algebraic expressions that look different, but when you substitute values of x or n or c or whatever the variable is into them, they give you the same value for both, all right? What we saw today was ways that we could use the distributive property and factoring to produce equivalent terms, or equivalent expressions, sorry, and how we could also combine like terms. Like terms are ones that have the same variables raised to the same powers, and you can combine them by simply adding and subtracting their coefficients. Pretty easy. For now, I just want to thank you for joining me for another NGen Math 6 lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.